Can someone just like for next lecture just be like, John, don't forget to record because
Yeah, okay.
I just lost the first like 10 minutes. I'm so sorry.
All right,
So
Lamek's in charge of that.
okay, Lamek, you're gonna be the
I volunteer
recorder.
myself as treasurer.
Okay,
Like,
thank you.
Out of
All right.
bag.
So we're talking about partial fractions, and we're talking about this example and this idea of LCD. And this idea of factors comes into play, right? If you think about it, 2 and 3 are separate factors, and we need to multiply by like the different factors that appear. In our second example with the x plus 3 and the x plus 4, we got to multiply by the missing factor, right? So like, and then like yada yada yada, you get to the answer, right? So just kind of keep that in mind. That's the idea here. So we got to identify the missing factors to kind of help us get to our final answer. So what happens now? What happens now when I reverse it on you guys? What happens if I reverse it on you? I tell you that this is what I ended up with. Sorry.
I remember this.
So let's say I ended up with this. Well, how can I try and figure out what I started with? Do you guys see the question that I'm posing here?
Yeah.
We're just
I remember having to do this.
I remember. Yeah, I remember. I did.
Are you guys from BC? Is that why?
completely.
I'm gonna assume you guys are from
No,
BC.
I did this in AB.
No, I did AB. I did an AB.
Yeah, I did this in AB.
Yeah.
That's crazy. Okay, cool. All right. Well, so the idea is I have to figure out the 2 pieces that it came from, right? How do I know that there are 2 pieces?
Because of the denominator.
Yeah. So I see that there are 2 factors. So it had to have come from 2 pieces, just like this example here, right? If I were to combine these, right, in my final answer, I would get something with x plus 3 times x plus 4. I mean, I don't know what the top is. I can figure it out. But what I'm saying is I know that because I have 2 pieces here, I started with 2 pieces. Does that make sense?
Yeah.
So let's kind of assume that. Let's assume that the first piece had a constant on top. I don't know what the constant, like the constant on these were like 1, right? But it had a constant on top, and the bottom piece is the first factor. And then I'm gonna write plus b over the second factor. Right? So
Yeah.
A and B are my unknowns. I gotta figure them out and see how the fraction broke down. All right, well, from here, it's just algebra. I don't know if you see it yet. Maybe you'll see it on the next step. But what we have here is actually a system of equations that maybe you guys aren't used to seeing. But there's like 2 unknowns that we need to solve for. So let's see here. Let's what are we gonna do? Let's multiply everything by the LCD, by the common denominator that they all share. So I'm gonna multiply everything by x minus 3, x plus 1. So what am I left with? On the left side, right? These cancel out with this. I'm left with 7x minus 13 equals. This one is only going to cancel out with this, leaving me with the other factor. So I get a times x plus 1. Please let me know if I'm going too fast.
Yeah, how did that even happen?
Okay. So on this step, on this step, right, I'm taking this and multiplying it.
Okay, yeah.
Everything, right?
Yeah, I get how like that the left side of the equation, I get how that canceled out, but how did you just singly cancel out x minus 3?
So I have a over x minus 3 times x minus 3 times x plus 1. So the x minus 3's cancel out, leaving you with a times x plus 1.
What happened to the b over x?
Oh, I'm not there yet. I'm not there yet, bro. Why are you rushing me?
Oh, okay.
Don't rush me.
Makes sense. Makes sense.
Well, I'm taking one piece at a time. We went the left piece, then we do the middle piece, and we do the right piece, right? Yeah. All right.
Yeah.
Plus b times. So something similar is going to happen here. The x plus 1 and the x plus 1 go away, leaving you with b times the other factor. Now, this is going to be kind of a shortcut. After you do a couple of these problems, you're going to be able to see that a pattern, not a pattern, but like That's kind of a pattern. A pattern will kind of emerge, right? Like it's always going to be a times the other factor plus b times the other factor. Does that make sense, right? Like if it's
Yeah.
like a over x minus 3, then it's going to be a times the other factor in this case, which is x plus 1, right? So this, you can always just like kind of jump to this step if you're given like a partial fractions problem, right? So here we go. I still have two unknowns, right? I have an a and a b I want to solve for. I have an A and B that I want to solve for. Lamek, I'm just going to mute you real quick. All right. So I want to solve for A and B. And then, so the idea is, well, what can I do? What can I do to make sure that like one of the things will cancel out and I can solve for it? You know what I mean? Well, if you notice, I have a common X in on both sides of the equation, right? So that X, it's going to be the same for whatever value I pick for X. I could pick X to be 5. I could pick X to be 0. I could pick X to be 1,000,000. I could pick X to be a fraction or something like that. What I need to do here is choose a smart value for X. I need to choose a smart value for X. What do I mean by smart value? Well, if I plug in, let's say, I don't know, 0. If I plug in 0 for X, will that eliminate one of A or B? In this case, no, it's not going to, right? A and B are going to stay alive. We need to kill off one of them so that we can solve for them. Do you see what I'm saying here? So I'm not going to pick 0 for X. I'm actually going to pick, this one's going to tell me I'm going to choose X equals -1. That's going to be my first choice, right? I'm going to set X equals -1. Why am I doing that? So I can kill A, right? Leaving me with B to solve. So watch what happens. I get -7 minus 13 equals, the A part goes away, B times 1 minus 3. And look, I only have B to solve for now, which is, and it's just an easy algebraic equation, right? This becomes -20 equals oh, that's not right. Wait, is that right? It's -20, right? Yeah, -20 and then
B
-2.
times -4. Yeah. Yeah, -2.
It's supposed to be a negative
Wait,
1.
isn't -1? Yeah, you put 1 minus 3. It's supposed to be -1 minus 3.
There it is. Okay. Good looks, good looks. This becomes -20 equals -4B. There it is. Okay. And B is 5. It's crazy, right? Like you guys know all of this calculus information, and yet it's going to be the algebra that trips you up. Hopefully not. Hopefully not. Hopefully not. That's not going to.
It happened a million times. Million times.
I swear, negatives are the worst. Negatives and exponents get everyone. It's crazy. All right, so look at that. I figured out my B. Now let's figure out my A. I'm going to choose another smart value for X. What do you think the other smart value of X is going to be in this case?
3.
3.
So I'm going to set X equals 3 and set up my equation. Why don't you guys do the same while I do it? A, this is 8. I think it's 8. Did you guys get 2? I'm getting 2. Okay.
Yeah.
Okay, cool. I see your thumbs up, Oscar. Thank you for that. All right. So what did we just do? What did we just do? We just figured out the two pieces that the initial fraction came from, right? So watch. Let me kind of recap here. 7x minus 13 over x minus 3, x plus 1. This, we can say now, right, that this is going to equal my a, which is 2, over x minus 3, plus my b over x plus 1. One really big pitfall that a lot of people end up kind of messing up a little bit when it comes to partial fractions is it's actually a really small piece, but the initial a and b. I usually get this question, John, does it matter if I do a over x minus 3 plus b over x plus 1 versus a over x plus 1 plus b over x minus 3. It's like, does the order matter? No, the order does not matter. But this piece does. This guy right here does. If you were to flip the order, right, notice that like the answer would just still be the same, and just the order would be slightly different. You see what I'm saying? So please make sure you keep an eye on which one is my A value, which one is my B value. Because if I were to flip it in the beginning, these two results would actually be flipped too. It would still get me to the same answer, an equivalent answer, just the order is just different. Okay, so no, the order does not matter. Just make sure your variables are consistent. Okay, I would write that down. Okay. Keep an eye on your variables. All right, keep an eye on your variables. Make sure your work is consistent. All right, so that was my little spiel on that. So what was the point of this? Why did we just do that? Well, let me show you. What if the question was,
Wait, I have a question. So, it's an equation.
Carlos, you sound like Electro from Spider-Man. I can't hear you, man. You're not coming through clearly.
I'm saying when I did it like last year with my teacher.
No, it still sounds broken.
It's
Really, really broken.
double check your mic. Sorry, man. Maybe just
Rejoin the
type it
call.
or rejoin. See what works. Anyone have any questions so far? No?
Yeah, John, is there like more than one answer to the problem? Or is that just like what's it called? I don't know, so it's like you picked a certain X value to like kind of work for you. So
Oh, I see what you're saying. So on this step where you have to like choose a smart value of X, it should not matter what value of X you choose. In fact, if I were to pick two other values of X, like I can actually set up a system and solve it that way if I wanted to, because I would have an A and a B in two equations that I can line up and then use elimination, substitution, whatever. So the reason why I chose these particular values of X is because it cancels out so easily, like one of the variables. So it doesn't matter what value of X you pick, you should get to the same answer for A and B.
Okay.
Hello, John. I have a question still. So last year, I don't know if you guys hear me better, but last year when I did it with my teacher, we did like a system of like equations where I would do like A plus B is equal to like 7, and then I would do like -3 minus A is equal to 13.
Whatever way you're more comfortable with.
I got a different answer though. I got for B is equal to 3 and his A is equal to 4 though.
That doesn't sound right then. You gotta maybe check your work. I know what way you're talking about. It's like you're setting up a system and stuff like that. But the A, like I said, the A and B should be the same value.
Always?
Yeah.
Okay.
Maybe if you want, like screenshot your work and like send it to me as an email, and I'll take a look at it later, and then I'll get back to you on that one. All right.
There's a question in the chat.
Oh, this method works for binomials, trinomials, and so on. Oh man, who asked that? Harry? Oh God, what a great question. Oh man. I won't be able to get to it. I won't be able to answer that question fully, but no, this method is if you notice, it only works when given two binomials, right? What a good question, man. Oh, if you look in the section, they actually go through all the cases. So, okay, hold on. You're jumping the gun, man. Let me finish this problem, and then we'll get to your comment. All right. Thank you, Harry. All right. So, going back to no, don't be sorry. It's a good question. Going back to the point of this, why are we doing this? Well, if I put that into an integral, right? Do you notice anything, right? Like if I were to, in fact, it'll probably be given to you as I'll multiply it out. This would be, it would probably be presented to you in this way, right? And you'd be like, okay, let's see. Well, how can I integrate this? Can I use u sub on this? and you would say, anyone? No.
No.
Why not?
No.
Why is the answer no? The answer is no, but like why?
Yeah. Because you can't completely take it out from the 7x minus 13.
I think I know what you're trying to say.
Yeah.
If you derive the bottom piece, you get 2x minus 2, which does not appear anywhere in the problem. You have 7x minus 13 on top, right? But not a 2x minus 2. So you can't use u sub. Can I use integration by parts?
I'm guessing no.
No, the answer is no, I can't.
No, yeah.
Because yes, I have two functions, but you
Like
can't, there's no u and v dv value or choice that'll come out clean, like that'll work nicely, right? So essentially what I'm saying here is like when given integral problems, you have to kind of run through like almost like a robot. I hate that, but you have to run through your toolbox, right? What method can I use that'll work for this? So this one, because you see that the bottom factors nicely, that right away that should tell you this is a partial fractions problem. Does that make sense? Because watch.
Yeah.
Since we did all the work already above, I can rewrite this as integral of 2 over x minus 3 dx plus integral of 5 over x plus 1 dx. And do I know how to integrate those two pieces?
Yeah.
Yes, I do. Okay, or you do. You better. Okay. If you have an x on the bottom, we know that the integral of that is going to be some form of ln. Siobhan, I don't know why the system doesn't let me talk. Do you have a mic that works? Maybe it's not picking up your mic. It's not letting me unmute you. This is so weird.
Wait, go to the mute. If you hover over the mute thing, there's like an arrow pointing up. If you click that, it lets you select your speaker and microphone. Make sure.
Yeah, double check your
selected.
mic settings. Maybe that's it. Okay. Where was I? So we're now integrating the two pieces, the two partial fractions, right? So I integrate this first piece. This becomes 2 ln of absolute value x minus 3 plus 5 ln absolute value of x plus 1. Please, 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 please do not forget your absolute values. You need those, okay? I know a lot of you probably don't, I don't know, your teachers didn't teach you why the absolute values are so important. It just, for the sake of time, it doesn't make sense if you don't put the absolute values on there. It doesn't cover all of the x values if you don't put that on there, right? And then, of course, we need our plus c. And look at that. We did it. We just integrated by partial fractions. Cool?
Yeah.
Ah, man, I want to do so many more examples with you guys, but I just, there's no time. Oh, another pitfall that I see a lot of people forget. Watch out on the integration. Well, watch out watch out for chain rule. A lot of people always screw that up. Okay. For example, if I had like, if this was like -2, right, in front of that x, you got to account for that, right? Because there's a chain rule that's happening. So there's got to be a -2 somewhere that pops up in your work. You know what I'm saying?
Yeah.
You know what I'm saying? So please watch out for chain rule. This is one of the most common things that you will, or common like, trick problems, like gotcha problems that your professors will most likely use on you.
Wait, John, can you say that last part again?
With the chain rule?
Yeah.
All right. So if you're integrating, like, I'll just rewrite it down here. If you're integrating this, right, it ends up being 5 ln absolute value of -2x plus 1, right? But then you have to account for the -2, right? By dividing by a -2. So you get, so this would be negative. That's your final answer. Did I do that right? Yeah, I did that right. Right? How do I work? I just derive this thing and I should get that back.
All right.
Okay, that's what I mean. Any other questions before we move on?
You know?
Okay, so going back to what was it? Was it Harry? Harry's comment. They go through a bunch of examples in the book. I'm just gonna kind of, I don't know. I might put it in the video. I haven't decided yet, but I'll just kind of title them here. It's page 444. This is the I'm doing PDF pages, not the actual page of the book. So if you type in 444, it should bring you to this example. So example 3 talks about it's called repeated linear factors. And that means like when you have something like a x plus something that repeats in your denominator, you actually have to account for that because just look at the example. I might just put it in the video. So repeated linear factors, it's just a tricky problem. For this class, I'm not going to give you the tricky problems. If you know how to do like this stuff like this, the thing that we just did, then you're fine for this class. But for the fall, they go through all of these tricky situations, right? So that's example 3. Example 4, what was example 4? Oh my gosh. Long division, which I feel like I don't even think it's a thing anymore, which is crazy. They don't teach kids how to long divide.
I hate it.
It's
It's
crazy.
so much easier. Yeah.
The reason why they need it is because for this, you need to know how to long divide polynomials. It's on page 445. It's a really cool example. It's when the degree on top is bigger than the degree on bottom. You have to divide it. You're going to get a fraction, which you then can do partial fractions on. It's crazy. It's gnarly. I love it. Example 5 talks about irreducible and reducible. Don't worry about example 5. I'm not going to cover that with you guys. If they teach that to you in the fall, I don't know. I don't know if they're going to teach that to you in the fall. All right. Yeah. Okay. So those are the only ones that I'm going to talk about here. All right. But that's it for partial fractions. I kind of want to move on. I don't know. Okay. Okay, sorry about that. All right, so so we're gonna move on here. So 7.6. 7.6 is kind of like a recap of all of the methods that were covered from 7.1 up until 7.5. Right? Yeah. So 7.6 is probably where the majority of this homework is going to come from. It's just going to throw you problems, and you have to decide what method of integration is best. So I think it's a good idea to kind of like figure out, like kind of do like a think aloud and just write down like the thought process when given an integral. So what I mean by it, so it's like when given an integral, right? Your first thought, holy crap, oh no, it's an integral, oh my God. No, your first thought is, does it have trig in it? Right, and that's from section 7.2. Second thought should be, I guess there's no particular order. Can you use sub? Right, I didn't cover use sub with you guys. I assume that you guys know it by now. Yeah, so use sub, it's like you have to see the derivative of a piece appear somewhere in the problem, right? That's how you know you can use sub, right? Is the integrand a product of two functions, right? So that tells you integration by parts, which was 7.1, I think, right? I don't know how to write this one. Can you can you use trig sub? Meaning like, does the form match up one of the three cases that we talked about, right? That was 7.4. Someone correct me if I'm wrong. And then the last one is is the function rational And can it be broken down? And this, of course, is just what we just learned today, partial fractions. Right? So these should be the thoughts going through your mind when given an integral problem in Calc 2, right? Like, does it have trig in it? And can you use so, blah, blah, blah. Like, this is what you should be looking at, right? Just, once again, following the theme. Can I rewrite this into something that I can integrate?
So I had a question. It says, is the integrand a product of two, and then what does that say?
Oh, I'm sorry. That's my shorthand for functions.
Oh,
FCN
okay,
is
that's I couldn't make out like the second.
my phone. By the way, thank you guys for putting up with my handwriting. I know I'm just looking at it. It looks disgusting. Ugh, I'm so sorry. I didn't get the bamboo stick enough as a kid, you know? So that was my brother. You got that. All right. So that's 7-6. All right. I would definitely look at it. If you're having trouble with identifying what method to use, definitely look at 7-6. They give you some good tips and tricks in there. I'm sure China's going to go through a couple during recitation as well. All right. So that's it for partial fractions. In fact, that's it for the integration methods. But there is one more thing I have to talk about with integrals. It involves integrals and involves like the integration methods that we just talked about. We are moving on to section 7.7. And these are called improper integrals. Improper integrals. Whew. You guys good? Hanging in there?
Yeah.
Hopefully this isn't too boring. Can I get thumbs up from you guys just to check in and see if you guys are, well, there? I'm getting a couple. All right, it's good, it's good. Awesome. I realized too, I missed some people on the freaking icebreaker because they were like absent or they just didn't respond. So if that's you, be ready. I'm gonna ask you soon. Hopefully. All right. 7.7, improper integrals. So what makes an integral improper? What the heck is a proper integral? What? Well, what you've been playing with, in terms of like area, right? What you've been playing with, these are actually considered proper. It means when you have like a bounded region that you actually can find that deals with like finite values, right? But when you're dealing with infinite values, things get a little weird, right? And so they kind of made its own section called improper integrals, right? So what am I talking about? Well, let's say I have this function. You all should know this, right? And I'm only looking from, let's say 0 onward. No, not 0. That's not 0. What? That's 1. Sorry. 1 onward. And I wanted to know, well, what is the area under the curve as I go? Oh my God, I want to throw up. Infinity was disgusting. Oh my God, that one's even worse. All right, whatever. What if I want to keep going out to infinity and beyond? Right? What happens if I want to deal with this function? Because I know that this function is continuous for all real values, well, positive real values in this case, right? If this graph kept on going forever and ever and ever and ever and ever, well, what would happen? What would be the result? Well, would it just go to infinity? Because technically I'm adding an infinite amount of things, right? Would it go to a finite number? How does that make sense, right? So this is where things get weird, and this is why we need some special notation with improper integrals. So the cool thing about this is it takes the idea of limits and integrals and actually kind of like puts them together. It's pretty interesting, right? Derivatives and integrals, that was FTC, right? No? Yeah? Oh, okay, never mind. So improper integrals, we're dealing with infinity, so that means we're gonna need some limits. We're also gonna need our integral sign. So let's kind of put it all together here. If I wanna integrate this thing, I'm gonna go from, I said 1, right? So I'm gonna go from 1 to infinity of my function. In this case, it's just 1 over x dx, right? But this form, it's considered improper. It's not, this isn't, what's the word I'm looking for? This isn't mathematically correct, right? It doesn't, because our bounds need to be finite. I can't say x equals infinity. I always get this argument, especially when I'm teaching L'Hôpitals. People always say like, oh, it equals like, or no, what is it? Infinity over zero, or no, what is it? Infinity over infinity is like, I don't know. People always argue with me that like infinity is like a value that you can assign. In math, no, that is a no-no. But in physics, it's a different story. You can ask your physics teachers about it. It's pretty interesting. But yeah, like infinity, there's like different levels of infinity in physics. But in math, infinity is infinity. It's like that's it. Like there's no ifs, ands, or buts about it. Right. So because of this, we need to use different notation. And yes, I'm going to be really harsh on you guys with notation, because your professors in this fall will be just as harsh. Okay, so it's not. I'm not saying I hate you guys or anything. You know, don't take offense to it. I'm just trying to train you. Right. We need to use different notation here. So what am I going to do? I'm not going to say 1 to infinity anymore. I'm actually going to use some variable r. Okay, you can pick any variable you want, right? I could have picked J for John, L for Mick, or A for Ali, right? But you can pick whatever variable, but you have to make sure that when you write the limit as r goes to infinity, that it matches up. Everything else stays the same. And I carry this out the same exact way I would carry out a regular integral, right? It just now has a little bit more direction because we're talking about like area, like we now are talking about something, as opposed to before with the integration techniques, we weren't really talking about a specific area, but now we are. So watch, let's calculate this thing, okay? So please pay attention to the steps that I do. You must show proper work to receive full credit on your upcoming quizzes and exams. So limit as r goes to infinity. John, does that mean I have to write the limit on every single step? Yes, 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 yes. Okay, don't get lazy. Integral of 1 over x is ln of absolute value of x. Please, once again, don't forget that. We're dealing with a definite integral, so I'm going from 1 to r. Right? If you want to add brackets, you can. It's up to you. The next step, I compute, right? Upper bound minus the lower bound. I get the limit as r goes to infinity of ln of absolute value of r minus the second piece does not need the limit because it's only dealing with 1. So this becomes ln of absolute value of 1. You guys see that? Like the ln of 1 doesn't have an r in it, so the limit's not going to affect it. It's only going to affect this first piece.
Yeah.
Right? So watch what happens. ln of 1, hopefully you guys know,
0.
That is 0. But now we have a limit to kind of compute here. Well, what happens to ln as the input gets greater and greater and greater? If you don't remember, ln graph looks like that. It goes to infinity slowly, but it eventually goes to infinity, leaving me with this. Oh God, my infinities are gross. What does that mean? In the context of this problem, of this area problem, what does that mean? What happened? Anyone?
Wait.
Oh, I'm sorry. The answer we got was infinity. So
Yeah.
in terms of the problem with the area,
That mean the area.
The area is just going to be infinity.
exactly. So
Yeah.
what
Okay.
I kind of claimed it before, right? I was saying we keep adding up these Riemann sums, infinity. So that means we get an infinite answer, right?
Mhm.
But then the question I'm going to pose to you is, are we always going to get infinity?
No, it's gonna be whatever r is, because r is the variable.
Okay, that's a good guess.
Yeah.
Anyone else? What do you guys think? We actually have time to actually like discuss a little bit here. So if anyone wants to like guess, what do you guys think? Are we always going to get infinity?
Well, I guess, yeah, because like you're approaching infinity if you're approaching infinity every single time, then the answer has to be.
Anyone else?
I don't think you always get infinity, but I feel like that's just cheating because I know you don't always get infinity. I know.
I mean,
I think it depends on the bound.
I guess you can kind of think of it like that. Yeah, it absolutely depends on the bounds. I guess you can think of it like, why is he showing us this if it's always going to go to infinity, right? Why would this matter? So the answer is actually no. It doesn't always go to infinity.
Wait, John.
Yeah, Harry.
We have infinity.
So we're talking about in the case of a single line. If we were talking about like the the bounds being like for the area of a shape with two lines, then it would be finite, wouldn't it?
Well,
Is that what you mean?
I don't know. You're saying lines, and I don't know what you mean by that.
He's saying that what if two lines made a shape,
Uh-huh.
like then it wouldn't be infinity.
Okay, all right. So I think we're starting to get a little bit more specific here. Right. So kind of like, oh shoot, kind of like what I showed before, right? If the figure is bounded, then yeah, it's probably going to be a finite thing. So it really deals with situations where we're going off to infinity, right? Whether if it's going to hit a value or not. And you know what? I'll introduce you guys to the terminology now. There's two terms that we're going to play with. This one's called divergent. Okay, so the answers will always either be divergent or convergent. And this is actually diverges, converges. This is going to pop up later when we deal with series and stuff. Okay, but divergent just means it's going to go off to infinity or it doesn't hit a real value. Convergent means it'll actually get to a single value. Okay, so in this case, diverges to infinity would be your proper like final answer. Why don't I, do I have to, I'll ask Trina to do that one. Okay, why don't I kind of like answer the question for you guys? Hopefully this will work. Let's take a look at another example. I'm gonna use the same exact bounds. I'm just gonna tweak the function oh so slightly. Do you guys know what this graph looks like? 1 over x squared?
I believe I do.
1 over x squared looks a lot like 1 over x, right? But the graph it cambers slightly closer to the axes, and the bottom piece like jumps up. It looks like this, right? It's not perfect. By now you guys should know my graphs are terrible, but this is what the graph kind of looks like. It cambers in towards the axis a little bit more, right? Than 1 over x, and then the left piece just kind of jumps up. So watch. I'm gonna look at the same exact piece, but just for this slightly different function. You see what I'm saying?
Yeah.
Yeah. So the setup's going to be very, very similar. So watch. If I take the integral from 1 to infinity, 1 over x squared dx. Well, just like I said before, you have to watch, like make sure the notation is good. Okay, make sure your notation is good. Your notation has to be good to receive full credit. So in this case, I'm going to say the limit as r goes to infinity of 1 to r. And I'm just going to do this like I did the last one, right? 1 over x squared is the same thing as x to the negative 2. So how would I integrate that one?
Negative 2x. Oh wait, no.
X to
X
the
is negative
1 over
1.
1, yeah.
Add 1 to
Yeah.
the exponent, right?
Yeah, x is negative
Yeah.
1.
1. Yeah.
So it's going to be 1 over x, and then with a
Negative 1 over.
right? Because of the chain rule?
Yeah.
Or not the chain rule, the power rule?
Yeah.
Right? So we integrated it. We're going from 1 to r, the limit as r goes to infinity. Am I going too fast? You guys good?
Yeah.
Okay. I'm going to plug in my upper bound. I get the limit as r goes to infinity of negative 1 over r minus, I can just, like before, it's just a number. So I'm going to get negative 1 over 1. So this becomes positive. And then, oh my gosh, anyone see it? What's going to happen?
Infinity.
That is
plus-
equal to 0. The limit of negative 1 over r is 0.
That first piece is going to go to 0, leaving you with 1. What does that mean? What, in terms of the picture, what does that mean?
I mean, the area is 1.
That means as I go out to infinity, right? If I were to let that graph go all the way out to infinity and add up all the sums, I get a sum of 1. No? That should blow your mind. We're going out to infinity and we're getting a finite value. We're saying this converges. Isn't that crazy?
Yeah.
I know. I'm giving you a little taste of what a series is going to be like, because this is exactly what we're going to be dealing with, right? Seeing things go out to infinity, but still converging to a specific number or specific value. It's nuts. And then like converging to like specific functions. Oh my gosh, I can't wait. Can't wait. All right. Sorry. So this is a very, very special case. I'm going to have China actually go through with you guys. This is called the P series. All right. And this is actually also going to come up back with series because it relates. All right. This is all related to series. Because if you think about it, integrals are just series, aren't they? Because like you're summing up an infinite amount of stuff. So the P series stuff, I'll have China go through that with you. It's going to explain why this one converged while this one did not. Okay, it's actually pretty cool. It's a neat little ditty. The last example I want to go through with you guys is. Oh man, I was not ready for this one. 459. No, I don't like that one. Ooh, is it this one? 0 to 1/2. Oh, here we go. Okay, all right. This is example 9 on the PDF page 462. All right, this will be my last example for today. Anything else? I'll put into the video. Actually,
oh wait, before you move on, can you scroll up a little bit for one second?
Yeah.
I didn't get to finish writing. One second. You can go now.
Cool. All right. Anyone else? We're good? All right.
Yeah.
So improper integrals. Just because you don't see an infinity does not mean it's not improper. Oh my gosh, there's too many negatives in this sentence. Just because you see the infinity, no wait. Just because there's no infinity in the problem, it doesn't mean that it's not improper. Did that?
Okay. Yeah, you said that.
That makes sense, right?
Yeah.
So watch. Example 9 is a great example of that. 0 to 2 dx over x minus 1 to the 2/3. You're looking at this problem and you're like, that just looks like a regular integral. You know, I can use the chain rule on this pretty easily, right? Or the reverse chain rule on this, like U sub on this, and I can get like an answer, right? And this will all be hunky-dory. The answer is no. You have to pay attention to the function that you're given. Think about what this graph looks like, right? Think about what this graph looks like. X 1 over x is the one that looks like this. Oh wait, like this, right? Or whatever. It's the one that looks like this, right? 1 over x. But if it's 1 over x minus 1, that just means, you guys know, shifts, vertical shifts, horizontal shifts.
Oh, x can equal 1 because then it's undefined, right?
Right.
Yeah.
So, oh shoot, sorry. This is not 1. That's 1 over x. Sorry. The graph looks like this. Looks like that.
The vertical, I think.
Yeah, because it's 2/3. Sorry, I didn't see the 2/3. My fault. But that's what the graph looks like. And the question is asking us to find. Oh, it's a 2. Sorry. You guys see that? Do you see the problem with this?
Yeah.
What's the problem?
X can't equal 1.
X cannot equal 1. When you do that upper minus lower trick, when you integrate, you're assuming that everything in the interval is continuous and is plug-inable, right, into the function.
Yeah.
So if you were to do that on this problem, yes, you would get an answer, but it'd be the wrong answer. We need to use improper integrals for this example because of the discontinuity. Okay, so please watch out for that. So ideas? What do you guys think? What can we do now that we know how to do improper integrals? Like what can we do?
Gonna be like from 0 to infinity. Plus,
I would do limit as
Not-
r approaches
Wait.
1 from 0 to r, and then r to 2.
Who said that? It didn't show who said that on my screen. Is it Carlos?
I
Okay.
said that.
Okay, thank you. Yeah. So we're not going to infinity, right? Infinity is like all the way down that way, isn't it? We don't want to go down to infinity. We want to get as close to 1 as possible, right? So we're going to let r, in this case, the variable r, go to 1. And so what that means is we got to break this up into 2 pieces. The first piece is going to go from 0 to r. And then the second piece is going to go from 1 to 2. R to 2, sorry. You see how we're using limits to kind of get really, really close to like 1,
Yeah.
right? But not touch it. You know, that's the whole point of limits. So this is the trick. You've got to pay attention to what the graph looks like, and you got to pay attention to like where to make the break and all that stuff. Like, you know, because if the question was like from 1.5 to 2, we wouldn't need improper integrals, right? So you always got to pay attention to what the question is asking you, right? So from here you get dx over x minus 1 to the 2/3, dx over x minus 1 to the 2/3, and you just calculate. You got to see what you're going to get here. So how do I integrate 1 over x minus 1 to the 2/3? Right, my power is 2/3. It's negative. No. All right, well, for time's
x minus
sake,
1 to the power of 1 over 3 over 1 over 3. So like
times 3, right?
Yeah.
Right, because let me double check. 1/3 times 3. Okay, that cancels out. I subtract 1 from the 1/3, and that gets me negative 2/3. Okay, I'm good. I'm going from 0 to r. You know what? Just because I'm gonna say the limit's gonna go to the whole thing, right? Plus, you're gonna get the same thing, right? When you integrate 3 times x minus 1 to the 1/3. From in this one, it goes from r to 2.
Yeah.
And then I'm going to have like 4 pieces, right? The upper minus lower plus the upper minus lower. So here we go. I get 3 times r minus 1 to the 1/3. So that's the upper minus the lower, which is 3 times negative 1 to the 1/3. Plus, I still need the limit. Oh my gosh, it's 1. 3 times 1 to the 1/3, because I plugged in 2, minus 3 times r minus 1 to the 1/3. This is sufficient work. This is enough work. Okay, you don't have to do more, you don't have to do less, but this is the amount of work I expect to see on your papers, right? And then now you compute the limits, right? So this guy, anything with the r in it, you're going to compute the limits. The first piece, it looks like it goes to 0, right? Because as r gets closer to 1, this gets closer to 0 times 3, which is 0. So I get 0 minus, what is the cube root of negative 1? That's just negative 1, so that's 3. Plus, what's the cube root of 1? That is another 3. The last piece, let's see, as the r gets close to 1, it looks like this also gets closer to 0, right? So it looks like my answer is 6.
Conversions to text.
Whew. Oh man, a minute over time. But how is that? Is that okay? That's pretty much all of improper integrals. I don't think there are any other really big cases to talk about. I think the only other one is like this guy. Like if you have negative infinity to infinity, what do you guys think would be the fix for that one? Like if you have
negative infinity to 0 and then 0 to infinity.
Yeah, just pick a value in between and then just kind of compute it that way, right? So I would pick 0 because it's easiest, right? So you'd break this up like we did on that last example. right? And then use your R's, your limits, compute that way. But I think that's pretty much it for 7.7.
Yeah, okay.
Yeah. Once again, these are being recorded. Mike, please be my record guy.
Yeah.
But yeah, I think that's pretty much all I wanted to cover today. Great job, everyone. Please remember your due dates. Please remember your homework stuff, your quiz is coming up, all that jazz. I can stick around for anyone that wants to ask any questions or like, oh, hey, can you show that part of the homework or anything? But we're pretty much done. So I'll see you guys on Wednesday.
Have a great day.
You too, man.
Thank you, John. Have a good one.
All right.
John, I had a question.
All right,
Yeah.
thanks, John. See you tomorrow.
All right, see you.
Do you have any like practice problems from the textbook that we could use about improper integrals?
Improper integrals? Yeah, usually the ones within that
pages.
section, the exercises that's given, those are usually the ones to go to. I would usually I would pick around the area probably that China's probably gonna assign. So if she assigns like 13 to 16, I would take a look at like 10 to 12 and like 17 to 20, you know? I'll take a look around that area if you want to get that extra practice in. And then if you have any questions on those, yeah, definitely come by and see me.
Got it.
Mhm.
Have a good one.
You too, man.
Hey John, can you redo the part where you got 0 again? 'Cause I was paying attention. No, it's still
Okay,
there.
that's fine. You're talking about,
Like right in the towards the end, yeah, right there.
okay, those two pieces?
Yeah.
Yeah, so we have to apply the limit as R goes to 1 to the whole line now, right?
Yeah.
I don't need to look at these two pieces because they don't have R's in them, right? I only need to look at the last two, the first and the last piece.
Oh, so you substituted in the limit. That's how you did it.
Yeah, I let this R go to 0. I mean 1, and I let this R go to 1, and then I saw what happened, right?
Oh,
So
okay.
if this first R goes to 1, the inside of that goes to 0 times 3, which gets you 0.
Oh, okay.
And the same thing happens on the other side.
Yeah. All right. Thank you.
Anytime.
I'll go.
See you. Oh shoot, it's still recording.